And we have another problem at the screen, and that is something related to rate of cooling, perhaps Newton's law of cooling related problem. Let's see what the problem is. A copper ball heated to 50 degrees Celsius cooled down to 25 degrees Celsius in 10 seconds after being immersed in an ice hole, a big bucket of ice. How many seconds will it take for a copper cylinder of the same mass, and the metal is also same, it is copper again. How many seconds will it take for a copper cylinder of same mass? First was ball, that means a sphere, and second one is a cylinder. Same mass, but their volumes are different, their densities will be same. Okay, I will consider all these things. Same mass and same initial temperature. That is the simplest problem to solve with Newton's law of cooling. Same initial temperature to cool to 25 degrees Celsius. The height of the cylinder is equal to its radius. It's simple. We can remember the Newton's law of cooling in this form. Rate of cooling minus dt by dt. T is the temperature here. It is sometimes written as B1 plus B2 by MS MCV. Kuch bhi. MCC is the specific heat capacity, or if you wish you can write it MS, and multiplied by area of cross section. B1 and B2 are some constant. M is the mass, S is the specific heat constant, and A is the area of cross section. T minus T naught. T is the temperature of surrounding, and T naught is the temperature of the body itself, or people would like to call it simply in terms of like BA. All these things is simply written as B and BA T minus T naught or something like that. But as far as our problem is concerned, we have simply everything same, MS same, only the surface area of the bodies are different in different cases. In two cases, and that is described in the problem, the surface area is different. That means in our case we can simply write that our rate of cooling is directly proportional to the area of the body, surface area of the body. So dt is also same, dt in time interval delta t, or delta t by delta t, if we can write it, delta capital T by small delta t, that represents time, and upper delta T represents temperature. Then delta T is also same. So you can write here that the ratio of time taken in cooling cylinder and the ball will be inversely proportional to the ratio of their surface areas. That means this thing, delta T, if I can write, because it's finite, is inversely proportional to the area of surface area. And that means one time we want is how much time will it take to cool the copper cylinder. Just tell this time as, or just take this time as delta T, and copper ball cooling time was given, and that was 30 seconds, and that will be A2, that the ball's surface area, and that is the radius of the ball was capital R, so I can write it surface area simply as 4 pi r square, and in the denominator we need to write down the surface area of the cylinder, and that will be 2 pi r. R is its cross-sectional radius, this thing is r, and since its length is also equal to r, that means 2 pi r square. This cross-sectional area this cross sectional area is 2 pi r s r 2 pi rl, and this cross sectional area we also take, and because they are all in contact with the surrounding, and this is also pi r square and pi r square, so this is again 2 pi r square. That means the total surface area we got here is 4 pi small r square, where r is the radius of the cylinder. And then there is also a relation between a small r and capital R, because their masses are same, densities are same, so their volumes will be same, and that means I can simply write r by r, that will be equal to 4 by 3 raised to 1 by 3, because this I wrote because it is mentioned in the problem that the height of the cylinder is equal to its radius, so I can write like this. You can take your values, you can compare their volumes, and you will get a relation between their radii. So I got two relationship here. You can solve it and you will get something like t equal to, I can see that 10 multiplied by 3 by 4 raised to 2 by 3, and I don't know how much answer you will get. It is perhaps approximately 8.3 second. In case you want to match your answer, this is the answer, and this was the answer given in second. That was it is also in second, but it is an expression, and this is the exact value, and not exact, but this must be close to 8.3 second, approximately equal to 8.3 second. So this problem is also solved. So thank you very much for watching.